My name is JC, and in this video I'll be reversing the LaFarge's Crackme number 2. This Crackme is free to download from the crackmes.de website, however you will need an account. Also notice this Crackme is pretty old. At the time of this video, it's almost 9 years old. Now although it's old, reversing the key algorithm in this Crackme is going to be a great challenge for anyone that's new to the reversing field or x86 in general. Now I've broken this video down into 4 parts. The first thing we're going to do is simply analyze the program by running it and seeing the behavior. Secondly, we'll debug the program using Ollydbg and watch how it operates underneath the hood. Third, we'll spend some time reversing the key algorithm and how the program determines if we entered a correct key or not. And lastly here, we're going to write a Keygen for this Crackme, which will demonstrate our understanding of how the program's key algorithm works. So part 1, let's go ahead and start by extracting the Crackme. And now once it's extracted, let's go ahead and run it and see what happens. So the first thing we immediately see was the fact that it starts blaring some techno music at us. I went ahead and paused the video and disabled the system sound so we won't have that interfering. Now that that's out of the way, let's go ahead and put some information in and kind of play around with the program to see what happens. So I'll put in a username of JC and a reg code of 1337. So the first thing we do is we see an error message that says our username must have at least 4 characters. One of the things we want to do as we're going through this basic analysis of how the program operates is we want to make a notepad full of the different strings that we see. And this will come in handy later as we start looking at the binary through Olly or Ida. So this first one here is username must have at least 4 chars. Alright, so let's go ahead and work with that, and we'll make our username 4 characters long, and we'll try again. And we start getting error messages that that's not the right registration code. So again, we're going to record this because this will come in handy later. We can also see what happens if we leave no input. Okay. You can also try the About button, see the author's information, the date it was made, and then the Exit button works. So we have 3 strings of interests, and now, as part of our agenda here, we'll go ahead and move into debugging the program. So for part 2 of this video, we're going to begin by debugging the program. To do that, we're going to open up Ollydbg and load our program in. Right away, if you're new to reverse engineering or x86 assembly, this might be intimidating. A quick introduction to Ollydbg here. The windows that we have. In this upper left window, we have our disassembly view. In the right, we have our registers. The bottom right, we have our stack. And in the bottom left, we have the dump. So to begin, the first thing we want to do is definitely not go through this instruction by instruction, stepping through it till we see something of value. Instead, we're actually going to take some of the information we got from our basic behavioral analysis here, and what we're going to look for is the string nope from the nope, that's not it, try again error message. Now to do this, we're going to right click in the dump over here, select search for binary string, and in the ASCII column we're going to go ahead and write in nope. Now it's going to come in and actually show us right here, here's our error message. Nope, that's not it, try again. So I can actually right click on this address and go to find references. Now right here we actually see where Olly has identified this being called, and the instruction is a push. So what we can do actually is just double click it and right here we see it being used. And if we look a little bit above, we see a message where it's telling us that we've entered the right code. So obviously some condition is being evaluated to determine if the key code was correct or not, and then it's going to jump down here if it is, or it's going to jump down here if it isn't. So one of the things we want to do, since we know we can actually evaluate to this nope, that's not it, is we're going to set a breakpoint. Now to do that, I'm just going to hit F2, and it'll toggle the breakpoint so that when Ollie sees this instruction pass, it's going to actually halt the program and pass control back to us. So now I'm going to go ahead and start the program within Ollie. I'm going to hit play a bunch of times till it comes up and running. We hear the annoying theme song. Now what I want to do is I want to go ahead and just type in the name that I was using, JC, and then the registration code we're using, 1337. And go ahead and click check it. And then you can see Ollie went ahead and passed control back to us since it hit that breakpoint, that push instruction. So if we scroll up a little bit, we can actually see quite a bit of information that's been put in now that it's actually ran with some data. One of the things that we immediately see is here's our registration code that we entered, this 1337. We see right above it another string of numbers. Now these are being pushed onto the stack with this push instruction, and then right below it we actually see the string compare call. So it's going to actually determine whether these two strings are equal, and of course they're not. However, it's safe to assume that it's checking our registration code against the actual good registration code. So one of the things we can do to verify that is in our notepad here, we'll write down our username, and then we'll take down this registration code, 35688303117. So to test this, we'll go ahead and execute our program again. Make sure it's running, and we'll know it's running in the bottom right hand corner here if it says running. And we'll go ahead and copy and paste in that registration code and see what happens. So we get the message that, yep, that's the right code, go write a Keygen. So that tells us that string 2 actually contains the correct registration code. If we scroll up a little bit, we can actually see probably what looks like the Keygen. So from here, we know how to actually get our proper registration codes. Now one of the things that the challenge requires is that we write a Keygen. So in order to do that, I'm going to go ahead and pause this, and we'll go ahead and bring this program into Ida. One of the things that we're going to want to hang on to just as a guide here is that breakpoint we set. And I got to the screen by clicking the B up here, which shows me all the breakpoints I set. We're going to hang on to this address, which will help us within Ida, 4012 Delta Bravo. And that'll help us within Ida. We can go straight to that address and actually start working around in there. So part 3 of this video, we're going to reverse the key algorithm. In the background here, I've loaded up Ida Pro, and I've opened up our Crackme. Now, for those of you not familiar with Ida Pro, it is a disassembler. So it differs from Ollie in the fact that Ollie actually runs the code, and we can actually step through the code as it's running, and we can set breakpoints and inspect data as it's manipulated through the code. Ida Pro is different in the fact that we don't actually run the code. This is static disassembly, so we actually just see the instructions from the binary itself. So you might also be wondering about the look of this or the arrangement. Ida Pro organizes the code for us into these logical blocks, and then depending on jumps or calls, it actually generates these arrows that show us kind of control flow. So really quickly, jump right into this. The first thing we're going to do is open up our notepad and get that address that we pulled out of Ollie to orientate ourselves a little bit. And we're going to, inside Ida, hit G, and that opens up the jump context menu. We can go ahead and put in the address we want to go to, hit OK, and we're taken there. Now you can see that the layout has changed substantially. There's actually a function within Ida Pro as it interprets our program that shows us the layout of what essentially is going to be our key generation algorithm for this program. One of the interesting things we can do is come to the very top of this tree and find the actual name that Ida has given it. In this example, it calls it dialog func, and we can actually hit X, and this will give us a menu of our cross references. If we double click the cross reference, we can actually see that it takes us back to the first layout that we saw when we opened up Ida Pro. Now that we have it open, we can see essentially when it actually calls that function to determine whether we have the correct key or not. And it's down here with this push offset. So if we double click on it, we go right back into it, and then we can come back down to that address that we had, that 4012 Delta Bravo. And we can see that this is the logical block for our error message of a wrong key. Now we can see an arrow points to it, a green arrow in fact, and that goes up to this block. Now when you're faced with a situation like this where you have a block and two arrows point left and right of it, what we have here is usually a jump statement where, depending on the condition, if the jump fails we follow the red arrow, and if the jump succeeds we follow the green arrow. So here it's jumping based upon, obviously, whether our key was good or bad. As you can see, if it's good, it jumps over, if it's bad, it jumps over here to the one it titles Bad Boy, where it gives us the error message, nope, that's not it. If it is good, it comes over here to the message it titles Good Boy and gives us, yep, that's the right code message. So this essentially is the end of our keygen. So if we start working our way up, we start seeing a couple things. The first one is this arrow that points back to itself. Now this is indicative of a loop. So essentially what happens is the program flow comes into here, it starts working, and it's confronted with a jump. Based upon the condition, it has the potential to jump back to the beginning of itself and continue again, and over and over and over, and this is that loop process until that jump breaks and it comes down into the next logical block. If we go up, we can see some more of these loops, some more loops. What's interesting to see is this one actually has two arrows, one pointing down to the loop block and another one pointing down below the loop blocks, which essentially shows us that there is a way somehow to bypass this block. Not that that's very important right now, but it's just something to consider. So more of the loops, bypass, another loop over here, and the bypass, loop over here, bypass again. We keep coming up, we see more loops, and then the flow dramatically changes. So let's take a second to look at what we have here. Quickly my eyes see this username must have at least 4 characters, and then if we look up we see a red arrow, and then to the right we see the first block of essentially what starts our key generation algorithm. So with that, we can obviously determine that this block up here has some type of condition. If it doesn't meet, we get an error. If it does, it starts generating the key for comparison. So looking at this top block up here, we can actually start to reverse this a little bit. So let's try and figure out what the condition is exactly to jump between these two blocks. We have a bit of a hint here where it says username must have at least 4 characters, so we can use that. If we look up, we see this JA. Not sure what this is. We can always go to Google real quick, pop this in, and search for x86 jumps. And here's a page that shows us JA is jump if above. So knowing that, JA, so jump above, so if it's above whatever value, it's going to follow this green line down here, and if it's below, it's going to follow this red line into this condition. So when we look up a little bit more, we see a comparison, the CMP, and we see it's going to compare EAX and 3. That's kind of interesting. So remember that username must have at least 4 characters. It's going to compare 3 and EAX. If it's above 3, meaning 4 or more, it's going to come down here. If it's below, it's going to come down here to that error message. Now that we understand that condition, we're going to look a little bit further up and we see this call. Now you'll notice I have an Ida Pro script that actually colorizes some of my lines. So anything that's a call will have this pink highlight to it, and that's just to help me easily identify things. So we see this call to get DLG item text A. And now again, going to Google, if you don't understand what a call is, it's simple just to look it up. So what we're going to do is we're going to go ahead and type in MSDN for the Microsoft Developer Network and get DLG item text. Okay, and let's actually see what this is all about. So it shows that, slide this over a little bit, shows that we have a handful of parameters that we're going to pass this. Now you'll notice that Ida Pro has went ahead and labeled them for us, which is kind of convenient. Keep in mind that the calling convention places essentially the parameters on backwards, and this is just part of understanding how x86 and calling conventions work. But the first parameter here is HDLG, and then you'll notice that HDLG parameter is also the last one pushed on the stack, which is kind of counterintuitive at first, but that's more of a lesson in basic x86 assembly. Moving on, we see that there is something called LP string, and it pushes the offset of string to this function. So to look at that real quick, let's just see what that's all about. MSDN shows that this is the buffer that's going to receive the title or text. So really quickly, logically thinking, here we have an error message that's talking about the username. Right before that, we're actually getting the information to do the comparison, and right before that, we're actually pulling the information. So it's safe to assume that this is actually a get to get the username that we provide, and that username is going to be stored in this string offset. And then further down, we actually see it using string again, loading effective address into EDX. So that's not too difficult, and essentially that brings us to the very beginning of the key generation algorithm here. So we know that it's essentially basing the key generation completely off of the username. That's all the calls we see before we get into this long string of loops and conditional statements. So to continue on, the next piece here, we're going to actually break down into each one of these sub-processes here and examine them and determine exactly what they do and how they do it. Okay, so to reverse this, we're actually going to go between Ida Pro to understand the layout and how the code is positioned, and how we're going to utilize how clean the code looks, and then we're going to hop back over to Olly to actually roll through the code section by section and actually see it in action. So the first thing, we were looking at this where it loaded the effective address of string. So it's going to load the memory address of where our username is stored into EDX. And one of the things we can do is we can just put a comment there, move memory address of username to EDX. And that's a great way for us to keep track of this. You'll notice that it puts the comment right here. This is because this is just Ida's way of annotating the line for us as location. So all of these essentially have the same address. It just sticks it right here. It's not too much of a big deal for us. It's going to go ahead and push EDX onto the stack for us. It's just something to kind of keep in our mind here, that the next parameter on the stack that we can immediately reference is the memory address of our username. And then we make a call to strlen, if you're not familiar with strlen, to get you guys used to using the MSDN to look things up, we pop strlen in there. The more you do this, the more familiar you'll become with these instructions, and you'll just start to memorize them. So strlen, let's see what we have here. Here we go. Strlen, we're going to give it the string to be checked, which we did with that push, where we push the memory address of the stack, and the function returns the length of the string. So essentially, we're getting the length of the string, and most functions from Microsoft will stick that return data into EAX, which would make sense here because we have EAX and we're moving it into EBX. So now we essentially have the length of our username, and we're going to stick it in EBX. So now something kind of interesting to pay attention to is we're sticking a hard 5 into ECX. So this is a statically assigned 5. This doesn't change depending on the size of our username, what type of registration code we put in there. This will always be 5, whether I run it, you run it, independent of what data we put in. So usually you'll see these, especially how it's put in an ECX, as a counter or a threshold to meet. So essentially, if you did a for loop and you want your condition to go up to five loops, this would make sense. So we'll put a note here. So next two thing is XOR two registers against itself. If you remember the XOR instruction, this will make these registers zeroed out. So this is a quick little trick to just zero out your registers, which means we'll probably be using them in the next function. So again, my coloring script will also color XOR statements blue, and that's just so I can usually just spot those real quick. And it XOR specifically based on two values when they're different. So you'll notice it didn't color ESI and ESI, but it did color this BL and this byte offset. So looking at this a little bit more closely, we actually see this big loop arrow right here going back to itself, so we can determine that these 3 blocks right here are part of a loop. This jump right here, so some condition happens where we're required to XOR EAX with EAX, or essentially we have to clear out the EAX register. If not, if that condition doesn't exist, we just skip down. We compare EBP to ESI, and then we jump if below. So when we do this comparison, if we're below, we're going to go up. So this makes sense because right above we have an increment ESI. So we're going to keep doing this incrementing ESI until we compare ESI to EBP and they're equal, in which case we're no longer jumping below, and we'll follow this negative red line here to the next statement. So that's interesting. We're incrementing ESI and then we're comparing them to EBP. So EBP is going to have a number that we have to essentially rise to. If we look up, and the cool thing about IDA is it has context highlight, so I click EBP and it shows me all the other EBP. So if we go up the path right here, we can see that EBP is part of this move instruction where we stick EAX into EBP. And we already kind of reversed this a little bit, and we're seeing that it's sticking EAX in, and EAX was that username length we got. So if we come back down here and think again, we've XORed ESI against ESI, so we've cleared that out, so we're starting at 0, and we're looping through this over and over and over, incrementing one at a time until we get to the length of username. So that's kind of interesting. As we come up and we look a little bit higher, we see this jump not 0, and we'll ignore that right now. but we see we're going to move CL, which is that lower end of ECX, into this byte offset, and we're going to do the same thing. We're going to move BL into the memory address of EDX plus ESI. We're going to come up here and do a comparison of 5 and EAX, which is important because comparison has the ability to set the 0 flag. And this is important because below the two move instructions do not have the ability to set the 0 flag. And this is important because right below that we have a jump condition. So really this jump is evaluating based on this comparison, even though it's not immediately apparent because of these two moves in the way. So essentially it almost might be better if these guys were above this comparison. But anyhow, that's besides the point. We also increment EAX. So this is kind of interesting. So let's look at this a little bit more closely. So we're going to increment EAX. Remember, we zeroized it at the very beginning. We're going to increment EAX. We're going to compare it against 5. If it's 5, it's going to jump across. Remember, jump not 0. So we have compare EAX and 5. So let's go ahead and pretend EAX is 1 for this case. So 1 and 5. That is not 0. So it's going to jump not 0. And it's going to come over here and continue down. Now let's go ahead and pretend that EAX is 5. We've incremented enough loops to where we're 5. Compare EAX 5 and 5. That will make a 0. So jump not 0 will evaluate false. So we'll take the negative flag. And we'll come down here to EAX where we clear it out. And then we continue along our way. So when we think about this, EAX can never get bigger than 5. Once it reaches 5, it gets cleared out again. That's kind of weird, and it's very interesting. Why is that necessary? So why do we count 5, and once it hits, we clear it out and restart? Okay, so using that context highlighting, we have EAX highlighted, and we go up a little bit more, and we see EAX right here in this XOR instruction. So what we actually see is this byte offset. So knowing that EAX can be any number between 0 and 5, we see that we have this byte plus the offset getting XORed against BL. So that's important to us. So let's look. BL comes from up here, and it actually comes from CL. So we move CL into BL, and then we XOR that BL against this byte offset. And CL actually comes from ESI plus EDX. Well, now here's a great question. What's an EDX? So if we remember, if we look up here a little bit more, we have string loading the effective address of our string variable into EDX. So essentially EDX is holding the memory address for where our username is. We're going to add ESI, which if you remember down here gets incremented. So essentially we'll be moving each character of our username because we're incrementing, so left to right of our username into CL, one character at a time. And then we move that first character using the next instruction into BL. Then we're going to XOR it against some random byte offsetted by the number of iterations we've been in. We're going to increment EAX. We're going to see if we're at 5 yet. And then we're going to go over here to move BL into EDX ESI. So this is interesting because XOR is going to store the product of the operation. So when we XOR these two together, that result is going to actually be left in BL. And then we're going to put BL back in that first position of our string. So we're actually going to mutate the original data. And then we're moving CL, which is our unmutated good version of that character, into that byte offset. And if we look at the number, it's 406327, which is one shy of 328 offsetted with EAX. But keep in mind that we've, after the fact of the XOR, we've incremented EAX. So while this EAX was 0, we've incremented it to become 1. 1 plus 406327 will be 406328. So these two will be the same. So when you think about that, we're actually just sticking this, the good version, back into this byte array where we've been pulling from the XOR. So we've been talking a lot about how these 3 blocks work. Let's go ahead and comment these up so it's a little bit easier to understand. So this first one right here, this move ESI EDX, so we're going to put the ESI offset of our username into CL. So this is going to have a good version or a clean version of the first character into CL. And then we're going to move CL into BL. So place carve username in BL. Now this is where it gets a little interesting. We're going to XOR these two together. So it's very important that we understand what is actually here. So what's really great about IDA is we can just double click this and go right into it. So we can see that there are these single byte values. So remember in our 5, it would be this one, then this one, then this one, then this one, and then this one. And that's very important to us, so we're actually going to pull up our notepad right here, and we're going to record these values. So we have 0x AA, we have 0x 89, we have 0x C4, zero x FE, and 0x46. So these are our possible offsets. Remember, we could only go 5 in. So if I hit escape, it'll actually take me back where I was. And to put these comments in, I'm using a semicolon, and it'll bring up this comment text box. So I'm going to go ahead and put these in. Now this is interesting. This is the offsets of EAX. So with EAX 0, we're going to stay at 328, which was this guy. EAX is 1, so this guy would be 1, 2, 3, and 4. And then remember, on the 4th one, we're going to then increment after the fact, after the XOR, to increment to 5. And once we compare to 5, we're going to clear it out. So we actually never evaluate against the 5th one. So this is our increment EAX. We don't really need to comment that. That's self-explanatory. The comparison. This is just a check to make sure we are not out of XOR bytes. Now then, this is where we get a little bit more interesting, because it seems to be shifting around some of our characters. So if we remember, BL is where we have the mutated character. BL holds the XORed character. And we're going to be moving that into EDX plus ESI, which, if we remember, is that string memory offset plus the offset of exactly which iteration we're in. So this is going to happen for every letter of our username. So it's going to stick the mutated one into EDX plus ESI. So it's going to, where I had the username JCJC for that first J, it's going to stick that XOR value in there. Then below that, it's going to take CL, which, if you remember, CL is it's the clean character from the username because it hasn't been modified by the XOR, and that's why we have this secondary copy right here. Because if we didn't need to do this, it would be much easier just to move this offset into BL and then ignore this line completely. So we're placing our clean version of the character into 406.327 plus EAX. So essentially, right after we XOR the character with one of these key values, depending on which one we used, we're going to stick our character from our username that we just encrypted with that, or encoded if you will, with that XOR byte back into this ring of possible XOR key bytes. So moving down here, depending on if we hit 5 or not, so this is more of a jump if we have not hit 5 iterations yet. So if we hit 5, we're going to clear out XOR. Then we're going to increment ESI, compare ESI to EBP. So have we gone through the entire size of the username? And if not, continue up, or let's move on to the next piece. So now I understand that this can be pretty confusing. So one of the things we're going to do is leverage Olly, and we're actually going to step through this. But the first thing I'm going to do here is open up Olly. We're going to go ahead and terminate it. I'm going to open it up. We're going to hit rewind, which will take me there. I'm actually going to go to the specific place that I want to look at right here, which is 401.163, and I'm going to set a breakpoint, 401.163, and I brought up that go-to menu in Olly with a Control-G. So here is where I want to place my breakpoint, and I'm going to go ahead and hit play a couple times. We'll get that program running again. And I'm going to use a longer username this time, and I'm going to put my username as my name is JC. And we'll put our leak key in. So now we're going to check it, and we automatically hit our breakpoint. Now, it's important to kind of align things here so it's easier to read. And we're going to see that we do our first move right here at 17 alpha, which we have 17 alpha right here, and I'm just referring to the last 3. And I'm just going to put a comment, again, semicolon to put a comment in here. And I'm just going to put a comment here, start, so we can watch with our eyes. Now what's interesting, and I want to pull this up in the dump, is we're actually going to view ESI and EDX. So I'm going to just hit go to or Control-G, just make sure you click on dump, and we're going to, actually we're going to have to do this after we tweak these variables or these registers a little bit. So we're going to step down. We're going to see we're pushing EDX onto the stack here. So you see that just got pushed onto the stack in the bottom right. We're going to call the stir length, and you'll see EAX will change when we do the call, and it's going to tell us how big our username is. And so it's A, which is a hex 10. So if we count out my name is JC, we'll get 10 characters. Now we're going to move that EAX into EBP, which we'll put right there. And you'll notice that the registers change red after they've been manipulated. We're going to clear out ESI and EAX, and then we're going to get right here to our start. We can also look right here in the middle, and it's going to evaluate things for us. Now something very interesting is we have in DS is Y, which is a second character. So it actually, this is very important, it strips off the first letter. And I'm not entirely sure why it does that. If anybody's watching this and they know why it does that, please try and contact me and let me know, because I've been racking my brain on that one trying to figure that out. Moving on, now that we do have values in ESI and EDX, we're going to go to ESI plus EDX. We really don't need the ESI because it's 0, so we can remove that if we want. And we're taken to the hex dump right here that shows the data inside this memory address, which is 40634A. So now we're going to move it into CL, and you'll see the lower byte of ECX is going to be manipulated, where it's going to put that 79 in there. And there it is. And then we're going to move that 79 into BL. There it is. And then we're going to do our XOR. Now, this is where things are going to get manipulated inside BL. So we're going to XOR, and it shows us here the value of this pointer, which is AA. So we're going to XOR BL against AA. And again, that gets stored where BL was. So this D3. So if you're having a little bit of trouble with why I'm calling it BL and I'm pointing to the EBX register, this would be a good time to pause and take a refresher into how registers are broken out. Really quickly, if you just need a refresher, EBX is going to address the whole 32 bits, where BX will address the right 16 bits. And then you can split that last 16 bits up into two sides. You can do BH, which is B high, which is the upper 8 bits of that right 16-bit side, or you could do BL, which is the lower 8 bits. And the 8 bits make a byte, which is 2 hex digits, and that's why we just see these last right 2 being manipulated. So now we're going to increment EAX. Okay, so increment EAX. And now we see EAX is turned to 1 up here. And we're going to compare EAX to 5. So EAX is 1, so this comparison will fail. And you'll notice the 0 flag. Over here is the E flags register broken out. Keep your eye on the C, because that will toggle when EAX is 5. And it'll toggle to 1, which will impact our jump. The next instruction here. Now this is where it gets interesting. We're going to move BL, which if we remember, it's the modified or post XOR instruction, so that D3 is in there in BL, and we're going to move it into EDI plus ESX, which we're sitting right at. So we'll actually see this 79 change to D3. And now it's D3, so we've actually mutated our username with this XOR value. Now the next piece, which is equally important, is we're going to move CL. If we remember CL, it's at 79, or our Y, so our still good version of our username character, into EAX plus 406327. So what we're going to do is we're going to go to that 406327 plus 1, which is EAX. So actually, let's just do this. EAX plus 406327. And we're going to move CL into there. Now, if you saw it up here, it changed to 79, which was what was in CL. So this is, if you remember, if I pull up our document right here, if you remember our string of keys, here was AA, here was 89, C4, FE46. So it actually takes the character that we just XORed and replaces its XOR key array with our character. So we'll do this a couple times. We'll go through this iteration a bit. So again, let's go ahead and move over to ESI plus EDX. So because I did that, it offsets us right here to N. So this is going to be the next character that it's targeting. So it's moving that N into CL. So we'll see that. Then we're going to move that N into BL. We're going to XOR it against the next key, which was 89. We're going to increment EDX, compare it to 5, and then we're going to move BL into the space. So we'll see this N down here modify again. And then we're going to modify our key string, which if we remember was EAX plus 406327, which is right here. 406 which is right here, 406327. Yes, it's right here. So we'll see that modify. So now it's 4E, which was that N. So if we do this, we're going to see that. So I'll just kind of go through it a couple times. Remember the last XOR key byte that we had was this 46, and you'll see that we're replacing it. We have this Y, N, A, M, and then the next one we should see in there is E. So we'll roll through it one more time. E. So now we've completely replaced the stock key array with the second, third, fourth, fifth, and sixth character of our username. Now obviously if your username isn't long enough, it'll never get to this point, which is why I chose a particularly long username. So now let's also go back to ESI plus EDX, and we'll see that we have continued to modify the username with those XOR keys. So we're going to go ahead and keep continuing to modify. Hopefully we understand how the XOR is working and how it's getting its new key values. So now that we're in the second iteration, we've already cleared out EAX once with this XOR EAX instruction. We've essentially begun encoding our username with XOR of bytes that were from the first part of our username, and we're XORing them against the second part of our username. So coming back down until we get to about here where we're going to compare ESI and EBP, where they're both 10, and you can see that both here at the registers panel and right here. Because of that, we're going to skip this jump statement, and that ends that first block that we were looking at in Ida. So essentially what we have happening, and this is going to come in handy when we begin building a keygen for this. So the first thing we're going to do is XOR the bytes of the username against those bytes. After each XOR, replace the XOR byte with the username character that it was XORed against. Now, there was also some that I said I couldn't figure out why it did it, so this is kind of the beginning. For some reason we ignore the first character of the username. Remember, because we had my name is JC as our username, and the program starts by grabbing the Y, and I couldn't understand the offset or why it would grab that and not the M. So moving down, we see a block that essentially does 2 XOR, so it's clearing out EDI and ECX again, and then it tests EBP. And if we remember, EBP stores a length of our username. And earlier I mentioned that this looked like a bypass. However, testing EBP against EBP and then jumping if below or equal, that'll always evaluate false, and we're always going to fall down into this, so there's no real way to bypass this to my knowledge. So it looks like no matter what, we'll end up falling in here, which is kind of beneficial since we don't have to add additional logic when we write our keygen. However, we do have to reverse this now. So looking at it, we can see some similarity from the last function we just came from. So we're going to move EDI, which we just zeroized, offset of this byte into BL. Okay, that's familiar to us. We're going to move EBP into ESI, so we'll be storing the size of our username into ESI. We'll be subtracting ECX, which was zeroized, from the size of our username. Then we'll be decrementing ESI, which stores the. So after we decrement ESI, we're going to move EDX, which was our now mutated from the above XOR username, plus ESI, which we just decremented, which we subtract, and so now we're one less, essentially, into AL, and then we're going to XOR AL and BL. So this looks pretty familiar. We're going to increment EDI, which we can see increments the order of this byte offset array that we were moving into BL, so that's going to be of interest to us. And then we move BL into EDX plus ESI. So we're going to move the XOR value back into the mutated username. So we're essentially mutating again and then moving that information back in. So this is essentially like the one we just saw, only there's something different with all these subtraction decrements. So we'll get into that in a second here. Then we move AL, which is that good copy, just like above, and we're moving that into 40632C. And just for giggles here, if we look at this, again, it's one less of this, and then if we take into consideration the increment EDI to offset the fact that we're essentially one off because of the incrementation, and we're moving that AL into that byte array, we're essentially replacing the XOR key with the mutated XOR value, which we just XORed again with the new key value. So it's starting to get a little confusing. We can see again another comparison to 5, so that hard 5, and then a jump. Depending on if we're 5 or not, we'll clear out EDI, increment ECX, compare ECX to the size. So this is essentially just the same above. However, there's something off about it with the subtraction. So let's take a look at it inside all. So let's bring up Ollydbg right here, and where we left off. So here's where we're clearing out EDI and ECX. We're testing EBP and EBP again. Then we'll jump down. So looking at this, just to orientate ourselves, we'll go ahead and consider this line right here the start, and I will notate it accordingly for our reference. So we'll go ahead and into action. We're going to clear out EDI and ECX. We're going to test EBP, and we're going to jump down here to the start, and this is where we get right into it. We're going to move EDI, which, if you remember, our EDI is 0, plus 40236D. So let's go visit that real quick. 40632D. So this 2B right here, this hex 2B. So this is actually our encrypted username right here. If we remember, the first letter of my username was M from my name is JC. And we see that M, because it was left unchanged for that reason that I never understood, we see the rest of the encoded string right here, with the one that it's referencing right now being this to B. So we're going to go ahead and move that into BL. Oh, I'm sorry, let's see here. Let's just go back and double check here. 40632D. I'm sorry. We were actually right here where this X is. So we move this X. I was slightly off. We move this X into BL, which this X is 78. So I'm sorry, ignore what I said a little bit earlier. We're going to move 40632D plus EDI, which puts us at 78, into BL. So in BL we're going to have a 78. And then we're going to move EBP, which was our size, into ESI. So we have an A in there. And then we're going to subtract 0 from ESI. And that's going to leave us exactly where we were. And then we're going to decrement ESI, which would put us at 9. So you can see our register changed here. Now then, we're going to go to EDX plus ESI, which EDX was our string, plus an offset of 9. Will put us right here. At the 65. So we're going to move this E, or the 65, into AL, and then we're going to XOR it against their key of 78, or X. So really quickly, let's take a visit over here to Ida. Go over here and let's just grab their key, which was, since they're doing the same 5 trick, we'll be using 78, we'll be using F0, we'll be using D0, we'll be using 3, and E7. So those are the XOR bytes that we'll be using. So back over here to Ollie. Now then we're going to increment EDI, which puts us at 1 in EDI. We're going to move BL, which is our again mutated byte, into EDX plus ESI. So it looks like we'll be moving 1D into this space right here where that E is. And now we have 1D in there. Do ignore the dots right here. I know there's data in it and it shows a dot. If Ollie can't represent in ASCII what that hexadecimal byte is, then it just leaves it as a dot. We're going to come down here, compare 5 against EDI. We'll be jumping. We're going to increment ECX up to 1. We're going to compare ECX to EBP, which EBP had our size, so this is going to tell us if we've gone through all the characters or not. And then we're going to jump back. So we're going to load up the next XOR key into BL, which right here looks like F0, which we recorded in our notepad. Here's F0. So let's continue. We'll move EBP into ESI. So EBP is 10. We'll subtract ECX, which is 1, from ESI, and then we'll decrement ESI again. So now we're working with the next one down. So if we move EDX plus ESI, we'll be over here to this 2E right here. So this will be the next one down for us. So it's loading 2E into EA, or into AL, sorry. We're going to XOR the AL against BL, leaving it in BL. We're going to increment EDI. We're going to move this BL back into our username string that we've been modifying all along. And that's going to give us a DE in there. So now this is, essentially this function is doing the same thing as the one before, except it's doing right to left. So where the one before was left to right, this one's going right to left. It's still rolling the key byte array again. And if we go a little bit faster here, and let's go to EDI plus 40632D. If we go there, 40632D. Actually, let's just go there. 40632D. Right here, 40632D. We can see that we'll be replacing their key string or their key byte array again. So as we roll, you see we're replacing it. So these are the ones that's default to the program. And then just like our function before, we'll be replacing E7. So we'll increment EDI. We're going to replace E7 here in a second. Right there. And now because we've replaced that key byte array completely, we're going to compare EDI to 5, and EDI does equal 5. So we will not jump. We will clear out EDI. We will increment EACX. We'll compare, see if we've done it enough times. We haven't. We're going to go back. And now keep in mind that we're going right to left against our encoded username, and we're going to start storing that into the their key byte array, and we're using that to XOR against the remainder of our encoded username. So hopefully this isn't too hard to track. It is a little tricky to think about, and that's kind of what makes this puzzle pretty fun. It's not hard to grasp, but it does take a little bit of time to sit down and look at how this works. So we're going to do that a couple more times here, and we'll be comparing. So you'll see this comparison ECX EVP. We've done this enough times that we've done this to the entire size of the username that we have. And then if we remember that we stick this in, our username actually sits in EDX, we can see kind of the final product of everything it's done to our username. So again, we start with M, which has been untouched by this so far, and it's done this to our username so far. It's replaced all the bytes that we've had in there with these double XORed bytes, which have been against its own key array, and then after the 5 bytes are exhausted, it starts using the first 5 of our username with the offset of that 1 character for the M. So so far it's pretty fun. Having a bit of fun with this. So we're not going to jump back, and now we're back to the next part of IDA, and we're about halfway done here. We've done this one. This is the one above has gone right to left, so this guy is XORing. I'm sorry, this guy is XORing left to right with those 5 XOR keys, and then R's of the username, and then this guy right here, these 3 logical blocks are going right to left. So let's just take a second and look down here a little bit further. It's clearing out ESI and EDI. And if we look, this looks really familiar again. In fact, this looks very familiar. This is almost spot on identical with the one right above. So I venture a guess that this is going to go left to right and do that same XOR trick. It's using the 5 for the loop. So my guess is it has only 5 bytes in its key array. And looking at the 2 moves that it makes with the clean version and the XOR version, it'll be overriding its key byte array again with bytes from our username, and it'll be writing over the double XOR encoded now, again making it triple XOR encoded. The only thing different here is this byte array. This is a new byte array for us. let's go ahead and hop in here and grab our next byte array. So 0x F7, 0x FD, 0x F4, 0x E7, and 0x B9. So to aid us for when we go to reverse this thing, let's go and make some notes. So we're going to XOR the already XORed username from right to left with these bytes per character. And when exhausted, and when each XOR is done, store the, what we'll call plain text for this example, plain text character in the key byte array. So we can go ahead and put a note right here. Looks like this, same as 1 with these bytes for the XOR. And we can simply go down, well actually we'll come back here. So here's the first one, so this is left to right, this one's right to left, and this guy looks left to right again. So we'll go ahead and grab this memory address to align ourselves, so 401 1D1. Go 401 1D1. And I'll go ahead and put a comment here so we know where we're at. Walk down. Again, it does that test EBP. I don't know a condition where that would evaluate, and we would actually bypass this. Now we're going to move EDX plus EDI, which EDI was our offset, which was 0 because we just cleared it out. EDX is our double XOR encoded username now, which we have right here, which EDX, so we'll see that 34A right here. There we are, 34A, so starting with E3, so we'll be moving E3 into AL right here. And then we'll be moving our, this is our key byte array that the program brings in again. And the CL, this is all old hat for us. XORs it, increments ESI. It's going to put CL into our double encoded, so this will now make it triple XOR encoded username. So we'll see this modify again with this next jump. See, there it's 14 now, and then we'll replace the first value in the key byte array with that first character that we just replaced. Compare it against 5, and this is working exactly like we've seen before. So we'll just fly right through it and one more, and that's it. So let's go ahead and hop back over here to Ida, and looking at this again, this looks again very similar to the second one we had. We see our subtractions, our decrements. Again, I'd venture a guess this is the exact same one going right to left, possibly a new XOR key array. So we have that right here, and this looks a little different. Not too sure where this came from. There's no references to it. Not too sure why Ida did that to our key array there, but no matter. We can essentially take, since it's a little bit hard to read, we can go 406338, and we can put it in our hex view here. So you can see we have this one BH, and we can grab our 5 hex characters right here. So we can just copy and paste those. So those are our 5, starting with that 1B. Oh, I'm sorry. Looks like we start over here at 337. Almost missed that. So here's going to be our keys. So we'll take those right there, clean those up a little prettier. And then again, this looks like same as 2 with these keys right to left. So what we can do is we can go ahead and just double check that. Watching this, here's our jump, so this is where we would align at. So you can see that. Here we are with the 1 Fox Alpha. 1 Fox Alpha. So we'll go ahead and run through it. And there's our EDI. So you can see EDI is zeroed out plus 406337, which had our B5 in it, which we recorded right here. It's being moved into BL. We're moving the size into EC, the size of the username into ESI. We're doing our subtraction. This is all old hat again, like the second XOR loop that we went through. And we can see it's, if we watch the hex dump, we can see it going right to left again as it modifies our username, and I'll fly through it a couple times. And then, just for giggles here, we should have hit 5 if I'm correct in EDI. Yep, we've already hit that. So what we should be seeing now is our pointer here to EDI plus 406337, which EDI was 1, so our offset, just as a spot check, if we look with our offset of 1, because 0, 1, 2, 3, 4, 5, right? I'm sorry, 0, 1, 2, 3, 4. If we look at our 1, this 1B, we should see 1B going into BL, and we don't, we see 63. So it's again overriding that key byte array with the byte from the username as it does the XOR. So we'll go ahead and fly through this again since we already understand it and reversed it once. And so we'll compare ECX, EBP, they're both 1, so we know we are done doing that function on the username. We've done every character. So that wasn't too bad. Let's see what's next in store for us. So if we just kind of scroll down a little bit, we can already tell that we're not going to be doing any more of those XOR loops because the format has completely changed. So another reason IDA is so great, we can easily spot check the flow here. So let's go ahead and dive into this. We're going to be moving this into EDI. We'll be loading the effective address of this. I'm not too sure what this is. 406345. We can hop over to Ollie real quick and find out. 406345. Let's see here. That byte is completely empty, so there's nothing there. So it's interesting. It's loading these a D word, which is 4 bytes into EDI. It's going to clear out EAX, EAX. It's going to test EBP, EBP again. Again, so we see that bypass, but I don't know a situation where that test will work. We're going to move 0 into 406345, which is odd because we already saw that there's zeros allocated there. No matter. And then we're going to jump into this next function. So this looks like it's going to be a little bit more fun, a little change of pace. So let's go ahead and look at it in IDA just a little bit, and we'll zoom in so we can focus in a little bit We're going to move EAX into ECX, and a little context highlighting here. We already cleared out EAX, so we'll be moving 0 into ECX. Now this is interesting. We're going to AND the number 3, so this is actually the decimal 3 here into ECX. I'm sorry, we're going to AND it against ECX. So it's important right now that before we continue that you understand the concept of bit masking. So the logic for AND essentially works like this, and we'll do a quick little introduction to this. So we'll do like AND gate logic, maybe truth table. If you're not familiar with this, you should stop and take a minute to check this out and how this works. Perfect. Oh, this is a worksheet for us, so we don't want to do that. Wikipedia will help save the day. Let me do it. Perfect. Here we go. Where's our AND? All right, here's the AND gate. So essentially, this is going to do some bitwise logic, and it's going to take the first bit and the second bit, and this is essentially just the way it works. There's no rhyme or reason. This is just how the gate works. It's built to do this. If both bits are 0, then your output's going to be 0. If one is 0 and the other is 1, your output is going to be 0. The only time that you're going to get a 1 is if both are 1. So if we look at a 3 in binary, and essentially it's just the right 2 bits. There we go, decimal. So we do a 3 here, and you'll see this is the binary. And since I have this right here, if you put any other value, so I'm going to copy and paste this, but let's go ahead and say we have 10, for instance, and we'll convert that, and we have binary. So we'll put our 3 right here, so that's the number 3. This is the number 10. I'm sorry for this on-the-fly demo, but essentially if we follow the AND gate logic, this will be 0, 0. Since both of these are not 1, it'll be 0, 0. We do have a 1 right here, and then a 0. And if you remember binary, that's the 2 position that it's in, so this will just evaluate with a numeric 2. So essentially, the only way that this will evaluate is whether this one is set, or this one is set, or both of them are set. So we could build this out something like, we'll leave these for reference, but so we could have that, which is 0. I hope I put enough zeros in there. Yep, 4 and 4. We could have this, which is 1. We could have this, which is 2. Or we could have this, which is 3. At no time could we ever surpass 3 because all of these other bits are 0, which using the AND gate will zeroize this. This is called a bit mask. So just keep that in mind. If you don't understand it, take a pause real quick and do a little bit more research on it. Once we AND it, so essentially what this is going to do is this is all, no matter what ECX is, so you can see ECX is whatever EAX is, and over here we increment EAX, and we're going to keep incrementing it until we compare it against EBP, which holds the value of the length of our username, so 10. What this is doing is it's never going to let it exceed the number 3. So it's going to be 0, then 1, then 2, then 3, which matches our dword size, which is that 4 bytes. So I'm already feeling that this is going to be a very similar trick to the last thing that we just saw with the XOR and how it's doing the different shifts. So we have EDI, which is holds the address of that D word, which was just that 4 0 hex digits, plus ECX, which 0 ANDed against 3 will be 0 because all the digits are 0, so nothing can be 1. So this will be the first position of EDI, which was 0 because we moved the 0 in there. We're going to move that into BL. Okay. The next thing we're going to do is load the effective address, LEA, load effective address of EDI plus ECX. So we're doing this, the address into ESI. So now we have the address of what we just pulled out into ESI. Then we're going to move EDX. Now EDX is important. Remember, that's our quadruple now XORed username, plus the offset of EAX, which was 0 for this first instance. So it'll be grabbing the first or the leftmost character of our username into CL. We're going to add, okay, so now this is where the mutation is starting to happen. We're going to be adding CL into BL. So we'll be adding the first position of our username, our quadruple XOR encoded username, into CL, and we'll be adding against BL, which, if you remember, was 0. Then we'll be incrementing, we'll be comparing, and then we'll be moving BL, which, if you remember, was well, we have to look up the we have to look up the add opcode, but essentially the destination will be BL. So it's going to add these two and then store it in the destination, or BL. So with the result in BL, we'll be placing BL into the offset of ESI, which was the effective address of EDI plus ECX. So essentially we're kind of doing what we did before with the XOR byte keys. However, now we're in step 5, we're doing the 4 from this D word up here. And whatever the result is, we'll be sticking it into that position with the offset. So now we kind of understand basically how this works. We could comment this up. Let's go ahead and do that. So EAX was our incrementer, so move count into EAX. So we'll do that. We'll and count against 3, so never exceed 3. So that's 0, 1, 2, 3. So 4 positions. From there, we'll move EDI plus ECX, which EDI was that D word. So move D word plus, I guess this would be our count ANDed into BL here. Then we'll be moving the same thing into ESI. Move address of above into ESI. We'll be moving EDX, so move EAX offset of this is our quad XOR encoded username into CL. So now we'll be add the character for the username plus the value in BL, and that is obviously going to change as we keep changing it here with this move statement. we'll be doing our increment and compare. So wait for 10. Username equals 10. So that's the logic behind that. And then this is kind of the magic of how this function works. Is will be move result, or I guess we should call this the sum, from add above into BL position. So the reason I call it the BL position is from where it pulls is EDI plus ECX, which is the same as the address of ESI, EDI plus ECX, which is where this gets moved to. So now that we understand it, let's go ahead and hop over there. So this 401.236. Come on. So we'll go 401.236. 401.236. Make sure you do this in the right window. We'll go on, orientate ourselves here, and also we see that D word. So we want to pay attention to that D word too. So we'll go there in memory, 406.345, and so there's our 4 null bytes. So let's go ahead and get going. So we're going to move EAX into ECX, which is 0. So ECX will hold 0. And now this is where we do our AND function. So you'll see that ECX is going to stay 0. Since we ANDed against 3, 0 is going to overpower the 1s in the bit mask. It's going to stay 0. And now we're going to move our offset of EDI plus ECX, which will be our 406.345 with this 00 right here into BL. So BL now holds 0. We'll do our addresses. Now we're going to get EDX plus EAX. So the first character of our quad mutated username into CL. So now let's add the two. So 20 plus 0, that's 20. So BL is going to hold 20. We're going to go ahead and increment EAX up there to 1. We're going to compare. That's going to fail because we haven't done this 10 times. Now we're going to move BL, which was our 20, and we're going to move it into ESI. And ESI, if you look over here, is 406.345, which is this right here. So now we have 20 in there. So keep your eye on this. We're going to keep iterating, and you'll see us keep moving. In the hex dump, we're going to move one more now. So we'll be moving that BL into the 406.345 plus ECX, which is, we'll be moving EDI plus ECX. So now we've filled up those 4 bytes right there. So this is important because we're going to add again. So now we're restarting, and essentially instead of doing the compare 5 or compare 4 like it was in the beginning, we're using that AND bit mask to keep us going back. So EAX is 4, so we'll be moving 4 into ECX. Now if you remember from the bit mask, and it's just kind of fun to do, here's 3 right here. If we do the binary 4, which is, let's see here, well, shit, that's 4 right there. Right. That's 4. If you remember the AND, if there's a 0 and a 1, it's going to evaluate to 0. So there's a 0 and a 1, a 0 and a 1, and a 0 and a 1. So we get back to 0. So it's a cool little trick they're doing. Again, this is why it's a great puzzle. It makes you think a little bit. So ECX is now going to be 0 because of our AND. So we'll see with this next step here. We're now at 0. That's great. Now this is where it actually gets a little bit more fun. We're going to move EDI plus ECX, which again is at 0 plus EDI, which will put us at this 345. So we have 20 now, and we're going to be loading our effective address in the ECI. That's not a big deal. That's for later. EDX plus EAX, so we're getting the next, we're getting the fourth position of the mutated username, and now we're going to add the two together. So now this is where we're actually adding stuff together now that we've populated the first 4 bytes. So A4 plus 2, 0. And I'm not going to do that in my head, sorry. However, we do get C4, and you'll notice that's BL here has changed. So we're going to go down. Again, we haven't done this 10 times, so we're going to miss this comparison. We're going to move C4 into this position now, so we'll be replacing 20 now. And we'll go through that. We should be able to make one more iteration after this. So you'll see us go. We're going to do that bit mask again, so now we're ANDing 8 against 3. So we should evaluate 0 again, and we do. And so now we'll be adding 78 in C4, so we keep going. So we're on the 8th position of the mutated username, indicated by EAX. Now we're on the 9th. We'll keep going here. And that's it, we're done. So let's go ahead and hop back over here to Ida Pro. So this was kind of a cool little function, and if you look down, we're getting really close to the end here. So the next thing here is we're going to pop EBP, and this is interesting, pop EBP. Let's go up here. Actually, really quickly, the only reason I'm going down a little bit is because I know there's a push, and I'm going to grab that for context highlighting. But I'm just curious what the last thing we pushed on the stack was. So we're going to scroll up till we find it, and we're going to see we pushed EDX, which was the string. So if you guys remember, at the very beginning of this, we made this random push where we pushed the actual string contents in EDX onto the stack. And now we're going to pop them into EBP. And remember, EBP was what we've been using for the size this time. So EBP is no longer going to contain 10. It's now going to contain our username. Okay, so now we're going to move hex A into ECX. That's important. We'll use IDA here. You could hit the H key, or you could just right click and go over here. And it's nice because it just rearranges it so you can see exactly what the decimal is. So we're going to be moving 10 into ECX. We're going to be moving this D word. Not too sure what's here. Looks like a zeros again, so this is already starting to look familiar a bit. We're going to move this D word into, I'm sorry, actually. Yeah, here, 406345. So here's where we were storing the sums of this previous function. We'll be moving that into EAX, so what we were just working with, we're going to be immediately using again. We're going to clear out EBX, and then we can see we're already in another loop right here. So let's take a look at what we're doing. The first thing we're going to do is we're going to go ahead and clear out EDX, so every time we're clearing it out. And we see a div instruction, so I'm going to take a minute here to actually bring us over to some x86 information. Not a lot of people see the div or remember the div or use the div, so it's important that we take a second to check it out. Div is interesting. Now let's see if I can find a good resource for it. Because it stores in both EAX and EDX. I used to have a great reference for it. This will work perfectly. Wikipedia again. So div, where'd it go? So div requires one argument, that first one there. So you'll see our div here is going to div ECX, and if you look at ECX, if you remember, we put a 10 in there. So ECX is always going to have this hard-coded 10 because we don't do any more changes to ECX. So we would understand that ECX change if we saw it light up here in this loop, but since it doesn't, it's always going to be dividing by 10. So back to this. This divides the value in the dividend registers by arg, so by 10, and the dividend register in our case is EAX. That's very important. So we'll be dividing by EAX. This is kind of where the magic is, though. The remainder is stored in EDX, and the quotient is stored in EAX. And you'll remember that right above we were XORing EDX out. However, keep in mind, if you look right below, we use the lower 8 bits of it in DL. However, we don't really do anything except test EAX, and this is going to be a little bit more interesting with this test. So essentially, when we so test is going to do an AND against EAX and EAX, and when it equals 0, it will. I'm sorry, when it doesn't equal 0, it'll jump. Okay, sorry. So with the test, it's going to test, so it's going to do the logical AND against EAX and EAX, and when it equals 0, it will go ahead and drop down. Until then, it's going to keep looping. So with that understood, we're always going to clear the remainder. Remember, EDX holds our remainder. We're going to divide EAX by 10. Add 48 to the remainder. The last, particularly the last byte of the remainder. And then we'll be sticking the DL into this. So it's important to understand that if this, when they do the addition, 48 plus DL, if you overflow into the next byte, they're only going to take the last byte, just the DL. So that's going to be important when we reverse. And coming back here, EDX 406549. So this is a new memory address. We haven't been here. So let's check this one out. 406549. We actually don't need that up anymore. 406, what was it? 406549. Oops. So this is an interesting thing, and this happens to me every once in a while, where I accidentally pop in the wrong address here, and this obviously doesn't do us any good. A quick trick to get us back is to exactly where we were, or where our current execution is paused, is just put in the EIP register. This always points to the next instruction that we're evaluating. So we wanted to go to 406, I forget it again, 549. So we see 406, 549. So it looks like 406, 549 is just an empty memory space we have right here. Take a look at that. We have EBX. So with this increment here, so we'll be just offsetting. So every single time we'll just offset by 1 down that address. Then we'll test that EAX. So let's go ahead and, this one's fairly simple. Let's go ahead and just execute it and see what happens here. So 406345, we'll move that in to EAX. Clean those two up. we'll divide ECX. So we're going to divide this register right here, EAX, by A. And remember, we'll be sticking the quotient into EAX and then the remainder into EDX. So here's our remainder right here. We have a remainder of 6. There's our quotient. Now we'll be adding 30 hex or 48 decimal to that. So now we have 36 hex. So we'll be moving 36 hex, which is that DL piece right there, into 406549. And there's our number right there, 36. And you'll notice that this is starting to populate. You'll notice that we're pushing, so this is kind of cool about Olly, is as we go, it's going to update and populate. So it's pushing this 406549 address into str length. So that's what's happening right here as we go. So if we keep going, you'll start to see this number push out and out and out. And you'll notice EAX is getting less. So we're waiting for EAX to get to 0, because then we'll be able to test EAX, and that will evaluate true. So now we will jump. We're going to push our new string, or that number, that 638.3611.214, onto the call there. And now we'll be getting the length, and that should be stored into EAX. So we got the length, and that is 10 digits. So now that we worked through that function, let's go ahead and look back at Ida here and see what's next. There was where we got the length. That one wasn't too hard. Now then, this one looks a little easier. So this looks like the last loop until we're done. We'll be moving EAX. Let's see here. EAX is zeroed from up here. So in order to ever pass this, this has to be zeroed. 406548. 406548. 406548. So we'll be moving that, I guess, which is 0. 406548. That's that. Into CL. And then we'll be moving CL into string 2 EBX and incrementing EBX. So EBX we zeroed up here. So we'll be moving this into string 2. Not too sure what memory address we move string 2 into. 406749, so that's where that'll go. And then we'll increment this and decrement. So this is interesting. When you start seeing this, what's happening here is they're decrementing EAX, so it's going to be working backwards. So essentially this looks like it's going to be reversing our numbers. So let's go ahead and take a look here. And we have our 406548 into plus EAX, or plus our 10, into, oh, that's what I missed. That's why I was confused. EAX is going to contain the length of our string. So we'll go ahead and put a note here. EAX has string length. Okay, that makes more sense. So 406548, perfect. So 406548 plus 10 will bring us out here, and we'll be moving that CL into string 2 EBX and then incrementing EBX. So as we decrement and go down EAX and down the number that we generated, we'll be moving it into string 2 and incrementing up the line. So let's go ahead and watch that, and I believe if we stay here, here's string 2 right here, so we'll actually be able to watch it populate as we go through this loop. And essentially all it's doing, you'll see it populating right here, essentially all it's doing is writing our numbers backwards. That's kind of the last trick of this. And we should have the 6, and that's it. and then it'll jump. So for that, we'll jump down here and we'll do our string copy, grab string 2 and string 1 and do a comparison, and then from there we'll determine whether this is correct or this is wrong. And that's it. We've fully reversed this. It's not too tough. You see right here, these didn't work. It's going to call string compare. It's going to jump down to it's bad. However, we did get our number, just like we did earlier in the video. So let's go ahead and bring our notes up to speed here. We did slack a little bit. So this right here, we're going to, fifth step, we'll be adding in a loop of 4. So that's 0, 1, 2, 3. A byte array of 0, 0. We'll be doing that after the 4th iteration, or after each iteration. Place the sum into the respective array position. So that one was pretty easy. The next one here is we take that 406.345, take that dword value, or the 4 bytes of sums, and divide them by 10, add 48 or 30 hex to the lower 1 byte of the remainder. Remember, that's important, because if we were to do it to the whole remainder, we might add more data than we would actually fit in this function here. Then move the last byte of the sum to actually this is a new array, and this will be the answer. And then lastly, we just have to reverse the answer to get the final answer. And that's it. That's the 7 steps that we need to do programmatically to our username to build a keygen. So with that, we're done reversing the key algorithm, and the next step here is we can actually go to writing a keygen. Okay, our last step in this video is to write a keygen. First off, thanks for bearing with me this long. For the keygen piece, it would definitely be a shame to let all this code go to waste. The guy took quite a while to make this, so I'm thinking probably the best thing to do here is we can actually take our value. You'll notice it's at our actual answer here at 406,549, and you see how he pushes this error message. He's got this nope, that's not it, try again, stored right here at 406.2 echo 7. Well, I'm thinking here we can take 406.549, 406.549, and we can just modify this instruction 549, reassemble that, and now when we run it, we'll get our error message, but it actually produces our actual registration code for the username that we put in. So one of the things that I want to do right now is I'll just go in here and take the breakpoints, go ahead and remove them. You could hit del if you want, or delete if you wanted to. Now with our patch completed, we'll just right click right here, copy to executable, all modifications, copy all. So here's our patched executable. We'll go ahead and save file, and we'll call this the Crackme Keygen. Save it. And if we come down here, open this up, I have a Crackme Keygen, and I have a feeling that music's gonna start, so just bear with. Actually, no, I did stop that music, so. Let's run it. Okay. So now we're going to type in my name is JC. Check it, and we get that number, right? We'll go ahead and record that. 35884298552. Go ahead and hit OK, and we'll paste that in there. That works. We'll type in anything here. We'll check it. We'll get that 377356139. That works. So, is it cheating?
You cheated. Pirate.
I'm not sure. But there's your Keygen. We just reutilized the program, all that guy's hard work. We did reverse it. And that's it. But yeah, that is kind of cheating for the Keygen. So since we took all that time to reverse it, I will show you this. I'm going to put a link to this in the my IDB file for Ida and GitHub. This is a Python. It's quite a bit messy, but this is my Python Keygen for this program. And I'm going to go ahead and save this in here. And I'll put this up on GitHub as well. Python Keygen. And essentially right here, I've pretty much built functions for everything. So it'll parse the username. It'll do that weird off by one. I wrote 2 XOR functions that takes the key list and the username. XOR left to right and then right to left. So I can call those twice. And then I have my add, where we did that add group, and the division. There is a piece in there where I do have to convert from big endian to little endian, so that's what this guy's for. Here's the number flipper. So after it gets the number, it just flips them. Here's all the calls to those functions. So essentially, once you take the parse name, you call R1, then R2, then R3, and each one is a parameter to itself. Then I have to do the division, big endian to little endian, and then I print the number flip. So we'll go ahead and do this, and we'll get that number right there. Bring this guy back up. My name is JC. And there it is. So I'll go ahead and put this on GitHub, so feel free to go through it, point out any mistakes, flaws, better ways to go about this. It was kind of lengthy. This is me just hacking away at it. under under 90 lines or under 100 lines. I feel pretty good about that. So apart from that, that concludes my video tutorial of the LaFarge's Crackme #2 from start to finish, including analyzing the program, debugging the program, reversing the key algorithm, and then writing a keygen 2 different ways. Thanks.